that good trick, you know, like right before it goes on. So, and the answer is. Okay. Let's see. So here's the function I think we want to use, and we have to verify that this is continuous on Q. That's going to be easy because if I give you any rational number, of course the value of the function is right there, right? And you can just prove from the epsilon delta definition that your function is continuous at Q. By the way, I need to emphasize, and the book does not say this in the back, but they're assuming that the domain is Q. So this is really x is less than square root of 2 and x is in Q. I'm just going to add that so that it's clear. We're only looking at rationals. Only looking at rationals. So the idea is if I give you an epsilon neighborhood around f of Q, your job is to convince me that you can find a delta such that anytime you are inside of a delta neighborhood of Q, the image of the function will be within this strip here. So can somebody tell me, given that Q, how would I figure out what delta would work? I need to figure out how much of an interval along the x-axis can I take. So would this delta right here work? If I'm within this huge interval, would it be true that f of x minus this point would be less than this amount? In other words, would the function be within this strip right here, if that's my delta? No, because I'm including enough of this portion over here that the function is going to be way down here, right? So what would I need my delta to be? Or how small would it need to be?
Absolute value of root 2 minus q.
Right, this distance right here really controls what delta should be, right? So you can, and remember your delta, we're not trying to do uniform continuity, we're just doing continuity, so your delta can have q in it. We usually call this c, by the way. It can have the point c or q or whatever you call it, can be in the delta that you come up with. Okay, so then it's easy to check that if you use that, then all of the outputs of the function, remember you're only plugging in rational points. All of the outputs, not only are they within this strip, they're actually equal to the value of that function because it's just a constant function on those points. Does that make sense? I hope. So that's proving that the function is continuous to begin with, from Q to R. Then you have to explain why it's not extendable to a continuous function on R. And it's pretty close to being extendable because I can just fill in all the points that we're missing on this section and fill in all of these points, right? But no matter what you do at the square root of 2, you won't be able to define, the issue will be, when you're trying to extend it to R, is what should that equal? What should you define it to be equal? I guarantee you, no matter what you try to say it's going to equal, it will not work. It won't be continuous. And to disprove the continuity of the new function that you get, you can do that using the sequences approach. Come up with two sequences that converge to the square root of 2. My advice is one of them should come from the right, one of them should come from the left, right? And do that in such a way that therefore the limit of the first sequence would be 1 because you're coming from the right, and the limit of the second sequence would be minus 1 because you're coming from the left. You get two different limits, then the overall limit doesn't exist. Make sense? Okay, so can I leave the details for you guys to work out? So the original function is continuous, just use an epsilon delta proof. We already talked about what delta should be. And then you just have to show me that it's, no matter how you try to define f of radical 2, the function could never be continuous there. It's impossible. Sweet? You good? All right, anything else on any of that stuff? pretty good about it? Just a matter of getting it written up, mostly, at this point. So glad we have Monday off. Kind of need a break, don't we? It's been a while. I have brought a few other problems to do. Are you guys interested in practicing on a few other problems just with the material we've been doing, or do you have too much else to do? Do you want to get the homework done? What's your pleasure? Want to see some more problems? Do you want to see more problems, or do you want to just finish your homework and call it a day?
I wish I could see both at the same time.
I could stand up here and do more problems while you're doing your homework. It's up to you guys. I'll do them if you want me to.
Yeah.
I'll do them? Okay. I may as well. I was going to say I could either do them or I could put them on the pop quiz next week or something. Okay, let me show you a couple examples. This won't take very long. I did them yesterday. That didn't take very long. Okay, just basically a couple of practice problems. So, just some good little practice problems here. So, here's what I want to do. Number one, show that. Oh, I'm gonna do the easiest one first here, so we can kind of move right through it. Here it is. Show that f of x equals 2x cubed minus 5x squared plus 2x plus 1 has at least two distinct real roots. So I ask you to answer that question, and does anybody have any thoughts on, so I'm finding solutions basically for that equation. Not asking you to figure out what the solutions are, I just want to know that there are at least two solutions.
Plug in a couple values.
Okay, what values do you want me to plug in?
0.
Okay, what's f of 0?
1.
1, okay. Give me another value.
-1.
-1, okay. F of -1 is, let's see, -2 minus 5 minus 2 plus 8. That comes out to 8, you said? It is a Saturday, so come on. -8, right? I'll do the hard math for you, don't worry. Okay, this is what they pay me the big bucks for. So, that value that way. Alright, so Josh, you're the one who wanted me to do that.
By the IBT?
Okay, by the intermediate value theorem, or if some of you may prefer to just refer to the location of roots, which is a corollary of it, but it's really just the intermediate value theorem. So, or location of roots. Okay, so by the intermediate value theorem or the location of roots, what can we say? And that'll be the open interval, because obviously, you could put closed interval and I would be okay with that, but the statement just says closed interval such that f of c is equal to 0, right? There's a root somewhere in between. What else should I have said before I applied the intermediate value theorem?
It's continuous.
Right, and why is it continuous? Right, okay, so note over here, f is a polynomial, hence continuous. Okay, so we get a root in the interval from -1 to 0. Alright, anybody got any other suggestions?
You plug in 1, you get 0.
Oh, how convenient. F of 1 happens to be 0. So there's another root, and it's not the same as that root. So we don't even need to do any more work. We're done. Okay? So we get at least two roots. Should put that one on the test, right? Pretty easy. The root comes right out. Just plug in the number, it's there. Okay, that's all you had to do on that problem. I told you these weren't going to be that hard. Let's try another one. It's a little more involved. Let's do this. Let's show that f equals x to the fourth is uniformly continuous on the closed interval from -1 to 2. This would be f of x. If you need to look stuff up, that's okay. Anybody have any thoughts here? Okay, we could just do it from the definition. In fact, that is what I want to do. Does anybody know a faster reason, though? Just right off the top of your head.
It's a polynomial, so it's continuous and it's on a closed interval.
Continuous functions on closed intervals are uniformly continuous. This is one of the theorems that should be on your flashcards. It's just theorem 4.4. Okay, so if you take a closed interval, then continuous is the same as uniformly continuous, and you already know that x to the fourth is continuous, so you'd be done. So solution number one is just use theorem 4.4. But that's not very helpful for practicing doing the work. So let's try to do it a little bit more brute force way. So solution number two. So Miguel's suggesting from the definition. And so the definition, let's see, does everybody know the definition? Let me just recall. F is uniformly continuous on D if and only if for all epsilon greater than 0, there exists a delta greater than 0, such that, remember, the delta is independent of the point that you're looking at. So this would be for all x and y in D with absolute x minus y less than delta, we have absolute f of x minus f of y less than epsilon. That makes sense? That's the definition. So if that's the definition, then how does this proof start? Right, let epsilon greater than 0 be given. So proof, let epsilon greater than 0 be given. How are we going to come up with a delta? Work backwards from scratch work, right? You do a little scratch work and work backwards. Okay, so let's do the scratch over here. So we're going to work backwards from what? This part here, right?
Yeah.
Yeah, so it'll be x to the fourth minus y to the fourth, absolute value, less than epsilon. Okay, great. If and only if. Okay, so does anybody see anything we can do? Okay, this thing factors. It's actually a difference of squares, right? It's x squared squared minus y squared squared. So how does that factor then in terms of difference of squares? X squared minus y squared and x squared plus y squared, right? Less than epsilon. And actually, the first part factors again, right? Actually, you know you're trying to get an x minus y out of it. So when you're thinking about how to factor it, that should be on your mind, right? So I'm going to factor this as x minus y, x plus y, and x squared plus y squared doesn't factor, but I don't need it to factor. So I just leave it the way it is. Okay? So far, everything is a totally reversible step, both directions. Okay, so what should I do next? Yeah, I mean, you really want to get, you really want to get x minus y by itself so that it matches up with the assumption here. So I'm just going to divide over the x plus y and the x squared plus, actually x squared plus y squared doesn't need absolute value bars, so I'm just going to drop them anyway. So I just do that. Okay. Can I let this be delta? No, because it is not a constant. So what you want to do is replace this fraction with something that is bigger or smaller? Smaller. I want to replace this with something that is smaller so that I can at least know that I will be, whatever I put here should be smaller than this. So that if x minus y is less than the smaller thing, it'll also be less than the bigger thing. Right? So I need something smaller here. Now how do I make fractions smaller? Well, I can either make the numerator smaller, well I can't because it's just a constant, or I can make the denominator bigger. So in what way could I make this denominator bigger? Right, I look at my interval here and I say, well, what values does x and y assume when I'm considering this problem? And the answer is it's on the interval -1 to 2. So the biggest that x plus y could be would be 4, right? And the biggest that x squared plus y squared could be would be, 2 squared plus 2 squared, which is 8. So 4 times 8, right? So it's just 32. Everybody following how we're doing this? It's really not that hard, right? It's actually not that bad. And so then this just becomes your delta now. Okay. So then you come over to your proof and you pull delta out of a hat like you knew it all along. Epsilon over 32. And now you just retrace the scratch. Well, you just assume xy element of D with absolute x minus y less than delta. Now retrace the scratch. Okay. And that will finish the proof. Pretty easy? Awesome. Okay. Any questions on that one? If not, I've only got one more. But the last one's the hardest one. But it's not that hard. I think all of these problems that I'm giving you, I've used on old exams before. So these aren't like super, super hard problems. They're kind of things I'd expect you to be able to do on a test. So here's the third and final one for the day, and then I'm going to leave you guys alone. Assume f is uniformly continuous on D with absolute value of f of x greater than or equal to some constant k, which is a positive constant. It's not 0. It's a strictly positive constant. And that's for all x in D. So every input in D has a positive output. Then what I want you to do is prove that g of x, which is defined as 1 over f of x, is uniformly continuous on D. Let's prove that the reciprocal of a uniformly continuous function is uniformly continuous provided that the original function is, essentially this is saying that your function is bounded away from 0. So,
Don't worry about it.
I'll get you on this side. There you go. So here's, the x-axis. You have k like that. So your function is either way up here or it's way down here. It's away from 0. It doesn't come anywhere close to 0. It's not just that it doesn't equal 0. We don't even have any asymptote that, the function doesn't do that even, right? It's strict, there's a wall there. There's a wall of width plus k to minus k, and the function just stays outside of that. Okay, so that's what's going on. Okay, so take a couple minutes, see if you can do this. From the definition. We got the definition, same thing we used on the last problem. Epsilon delta definition, I'll give you the first line of the proof. I like to be helpful here, Okay, that's how you get it started. See if you can take it from there. Is it still working?